Hello pre-calculus students, and welcome to our concluding video here on section 2.6, behaviors of rational functions. And before we get going on the example, I want to define what's called an end behavior asymptotes. So an end behavior asymptote is a function that describes the end behavior of another function. Okay, so the end behavior asymptote is a function that describes the end behavior of another function. And so a lot of times what happens in pre-calculus and in calculus is that you have a function that looks a little bit nasty or a little bit difficult to handle, like x to the fifth minus 1 over x plus 2. And sometimes you don't really care about the small little details. You really care about the end behavior, or the behavior in the long run, or the behavior as x goes towards infinity and negative infinity. So we want to find another function that captures the behavior of our function. And let's look at this example, and let's walk through this, and hopefully things will be a little bit more clear. So we'll start with finding the x-intercepts. Well, the y-intercept is just when x is equal to 0, so we'll substitute in 0, and I get 0 to the fifth minus 1 over 0 plus 2, and that's just negative 1/2. The x-intercepts is when you set y equal to 0 and you solve for x. And coincidentally, this just becomes 0 equals x to the fifth minus 1. 1 equals x to the fifth, and x is just going to be equal to 1. Okay? Not negative 1, because if you substitute a negative 1 for x, you're going to get negative 1 here, not positive 1. Okay? So intercepts are done. The asymptotes. Well, let's look at the horizontal. And in this case, we are going to use limit notation here. Limit of f of x as x approaches infinity is really the same thing as the limit of the leading terms. Okay, so we're gonna use leading terms to find horizontal asymptotes. So lead terms describe horizontal asymptotes. Okay. So it's the same thing as the limit of x to the fifth over x, as x approaches infinity. But x to the fifth over x is just x to the fourth. So notice here, I'm not saying that the functions are the same, I'm saying the limits are the same. So this is going to approach infinity, and I also know that the limit of f of x as x approaches negative infinity is also going to be equal to the limit of x to the fourth as x approaches negative infinity, which is also going to be positive infinity. So both of these are positive infinity. Okay. All right. So that takes care of the horizontal asymptotes. For the vertical asymptotes, we set the denominator equal to 0, so x plus 2 equals 0. X is going to equal negative 2. And before I write the limits for this from the left-hand side and going from the right-hand side, I'm going to need to see the graph to really get a much better idea. I can also do it algebraically, but at this stage, I'm going to rely on the graph just to get a better understanding, a better picture of the whole thing. So let's go to our TI 8384 here. And so in Y1, I'm going to graph the function that I had before, x to the fifth minus 1 divided by x plus 2. And some of you may wonder, like, how do I get a good window here? What I'm going to do is just go down to zoom fit, which is the 10th item in the list here. So go to zoom fit, okay, item 0 there. And it's going to take a basically somewhat of a wild guess, but it's usually a good guess on what this object is going to look like. And so you can see it starting to sketch in the function there. And I'm going to, you can see my window starting to take shape. It'll update in a minute. But I see that the Y window needs to be a little bit bigger, so I'm going to adjust that. And I'm going to go, instead of negative, and so you can see that as we approach -2 from the right, so from the right going left, the graph is going down towards negative infinity. And as we approach it from the left, it's going to positive infinity. So let's write these limits. So I'm going to say, use a different color here. The limit of f of x as x approaches -2 from the right, okay, that's what this plus sign here means, from the right, is equal to negative infinity. So let me show you one more time on our graph. Oops, there it is. So as I approach it, if I'm over here all the way on the right side and I slowly approach it this way, it's going to go down towards negative infinity. And then of course if I approach it from looking at this picture here, if I approach it from the left, so from this side, it's going to spike up to positive infinity. So let's update that as well. The limit of f of x as x approaches -2 from the left is equal to positive infinity. And you can somewhat see the contrast here. Let me use my mouse here to really highlight without messing with the screen. When we're talking about horizontal asymptotes, we're looking at the limit as x goes towards infinity and the limit as x goes towards negative infinity. When we're looking at vertical asymptotes, we are checking to see what's the limit as x approaches a specific number from the right and from the left. Now sometimes they might approach the same number, okay, but we are still going to look at it from the right and from the left as it approaches a specific number. For horizontal, we care about what happens as x goes towards infinity. Okay, so that's an important point there. So let's see here. We are asked to find, we haven't done domain and range yet. We got end behavior in here, and we got the asymptotes in here. So I'm going to erase some of this stuff, and then we are going to look at the other spots here. So for the domain, you can see that it's going to be at every single point except -2. So it's from negative infinity to -2, and from -2 to positive infinity. Now the range is a little bit tricky. Sometimes the horizontal asymptotes will exclude, if we have a horizontal asymptote, it will exclude certain numbers in the range. But from our graph that we have here, you see that everything is covered. Everything above 0 is covered. Everything below 0 is covered. And 0 itself is also covered, since we know that the X-intercept was at 1. Okay, so in this case, the range is everything, even though it has some asymptotes in there. Okay. So domain is done, the range is done, and now let's deal with this here, what's called the End Behavior Asymptote. So I'm going to erase some of this here, and let's look at that. So for End Behavior Asymptotes, we are going to use Polynomial Division. So we are literally going to divide this out, and it just so happens that this this format that we have here allows us to use synthetic division. So look back on the previous video. Synthetic division is allowed if the divisor is in the form x minus k. So now we can use synthetic division. So this is x to the 5th, and remember the placeholders: x to the 4th, x to the 3rd, x squared, x to the 1st, and then x to the 0th power. bring down the 1, multiply by 2, bring down negative 2, multiply by that, get positive 4, bring down the 4, multiply by negative 2, get negative 8, bring this down, this becomes 16, and then this becomes 16, this becomes negative 32, and altogether you have, this is the remainder here, it's negative 33. Okay, that's your remainder. So now this function, f of x, can be written as x to the 4th minus 2x to the 3rd plus 4x squared minus 8x plus 16 minus 33 over x plus 2. Okay. Now, one of the things that's so tricky for people to realize is that for end behavior, we really care about large values of x. So we know that as x approaches infinity, or negative infinity for that matter, this part right here, the remainder, will approach 0 because you're going to have a constant divided by a very, very large number. So as far as end behavior is concerned, or I'm sorry, end behavior asymptotes is concerned, we can ignore remainders. And we can just look at this function here. So the end behavior asymptote in this case is x to the 4th minus 2x to the 3rd plus 4x squared minus 8x plus 16. Okay. And some of you may be wondering, what are we doing here, or why do we bother doing this? And that's a very legitimate and good question to ask, because we have to see this in the big picture. Now, again, what I was talking about before is that sometimes you have a function like this that you have to deal with in the real world, but you don't really care about what it behaves like in the minor details. You really care about the large values. And in that case, dealing with one singular polynomial like this is a little bit better, a little easier to handle than a fraction of polynomials. And so let me show you on the graph why end behavior asymptotes matter. So I'm going to go into y equals, and I've already typed it in here to save us a little bit of time, so I'm just going to enable this, and then when I graph this, hopefully it'll be a little bit more clear. You can see the end behavior asymptote being drawn in there. Okay? And what this is saying is that in the long run, the function x to the 5th minus 1 over x plus 2, the blue graph, behaves just like the red graph. There's some detail in between here that's a little bit different that we have to deal with in the form of vertical asymptotes, and we've already written 2 limits to describe that. But in the long run, the blue graph behaves pretty much like the red graph, okay? And that's what end behavior asymptotes give us. Okay? Now, it's also a little bit complicated in some sense because of the notation and the vocabulary. We have end behavior and end behavior asymptotes. So I just want to sort of hammer home this point here that end behavior is dealing with limits as x goes towards infinity and limits as x goes towards negative infinity. Okay. End behavior asymptotes is a function. So it's a function that describes the end behavior of another function. In other words, if you look at the graph one more time, the red function, the end behavior asymptote, describes the end behavior of the blue function, the original graph that we were showing there. Okay? And so this sort of ends the lesson here. And the big idea you should get from this video, this lesson, is that rational functions have some interesting behavior. They have some strange-looking graphs and some limits in some of the minute details. But in the long run, they pretty much behave like any other polynomials, and that's kind of why polynomials make such a big deal. So thank you for watching here. As